That's right. Fission and fusion. We'll start with fission. Who knows what fission is? Yes. So not necessarily a neutron being fired. It can happen spontaneously. It's possible for it to happen spontaneously. I'm going to put a. So what Paul has described here is this this idea that we have a neutron being fired into some nucleus. I'll make that nucleus a bit smaller. Some large nucleus. That large nucleus splits into two. Oh, get rid of that, sorry. Splits into two smaller nuclei, and I'm just going to draw them smaller like that. Not necessarily the same size, but very similar in size, often, or rather similar in mass. And I'll write an equation in a second. And some neutrons are created. Actually, that's a little bit big. There. There's sometimes two, sometimes three, depending on the reaction you're talking about. Okay, so this is the parent nucleus. We're going to talk about this as uranium-235, and these are the daughter nuclei, these ones here. Of course, associated, as you will know, with the creation of a daughter nucleus, it might be created in an excited state, and we'll see the emission of some gamma ray photons. Of course, somebody asked the other day, is it two? Well, if they were both created in their excited states, then yes, it would be two gamma ray photons. These neutrons are created with approximately 1 to 2 million electron volts of energy, and that's key to understanding. So this is a neutron here. I'll say that neutron. So that's a fission reaction. Induced by that neutron being fired. It can happen spontaneously. This reaction can happen spontaneously. In this reaction, now here's the reactants here, this large nucleus and the neutron, and here's the products on this side. Okay, mass of the reactants is greater or smaller than the mass of the products? Yes. The total mass is what I was going to say. Total mass of the reactants is greater than the mass of the products. Where has that mass gone? Yeah, that's right. That's right. It's turned into energy, hasn't it? Turned into is energy. So energy is released in this reaction. Energy is released in this reaction. That's good. Let's have a look at a possible nuclear reaction. Neutron, we're going to say 235 uranium, uranium-235. Arrow represents a fission reaction. Xenon. Strontium. Plus 2 neutrons. 2 of them. Now, actually, don't put those last bits on there. We're only interested at this point in this reaction here. Okay, so have a look at the mass numbers on the left-hand side. Add up to 236. 140 plus 94 is 234.56 there. Okay, so the mass numbers are constant. 54 and 38 is 92. No problems. Okay. Charge is conserved. Mass is conserved there. That's good. Here's another example, just so you know that it doesn't necessarily happen like that. But it is induced fission again. 235.92 uranium. Here we have, this is tin. 132.50 tin. That's right, isn't it? It's called tin. Thank you. 101 and 42 molybdenum. MO, is that right? Molybdenum? 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 I thought it was pronounced molybdenum. I'm not sure, to tell you the truth. Plus 3 neutrons. Also a fission reaction. So from that you can say that fission will not always result in the same products. You'll have to repeat that question, Andrew, please. No, they will not. They what they'll tend to do is just ask you. So they'll give you the entire equation, and they'll leave one out, and they'll say selenium is created. Can you fill in its blanks? 132 and its mass number and its atomic number. That question has come up many times. No, you do not. No periodic table is given to you. It's not. Yeah, it's not necessary though. Yeah, if you think that you need a periodic table and you're not given one in the exam, it's because you don't need one to answer the question. Okay. You're not expected to remember these the chemical symbols or anything like that. So don't worry about that. That's not necessary. Calculate the energy release when the following nuclear fission reaction occurs. Here's a different type of reaction, of course. So a neutron is fired into 235 uranium again. This isotope of uranium, we get barium and krypton and 3 neutrons. Now, I'll just rewrite those mass numbers and atomic numbers. Can somebody tell me what we do exactly what's the process to solving this problem here? Calculate the energy released. Yes, Paul. Absolutely. So we're going to calculate the total mass of the reactants and the total mass of the products. Find the change in mass, or the delta M, this value here, and then we're going to put that into E equals MC squared. Okay. Remember, this is the mass defect. Now, let's see. Okay, so I hope, can you guys read that? Yeah, the minus 25, yes. Minus 25, minus 25, minus 27 there. I'll give you a second to have a go at that, please. Going to add the mass of the neutron. 675 by 10 to the minus 27 kilograms. Quiet, please. Thank you. Plus 3.9017, 10 to the minus 25, equals, I did these calculations. I'm assuming the book is correct. 3.91845. 91845 by 10 to the minus 25 kilograms. So that's the mass of the products, mass of the reactants, sorry. Mass of the products, barium. I'll take a bit more space here. Shh, please. Boys. Yes, we understand that the book is not perfect. I'm going to give you the right... Shh, shh. Please. I'm going to give you the right answer now, so it's okay. Shh. Thank you. 2.28 922 by 10 to the minus 25 kilograms plus, so that's my barium, my krypton, 1.57534 by 10 to the minus 25 kilograms plus 3 neutrons. 3 times this 1.675, 10 to the minus 27 kilograms. And we get a value of 3.91481. 91481, is that, so that yes is to confirm that you have punched that into your calculator yourself. 10 to the minus 25, yes, 25 kilograms. That's the mass of the products. Now, look at this number. They both have the same order, 10 to the power of minus 25. 91845 is larger than this number here. So I'm going to find delta M, the mass defect. Delta M equals this number, 845, minus 3.91481. Delta M is equal to 3.64 by 10 to the minus 28. That's correct? Yes, thank you. That's our mass defect. What happens to this mass? Turns into energy, or is energy. And so we're going to treat it as energy now. Thermal energy. Put it into Einstein's equation. Delta M C squared 3.64 10 to the minus 28 by 9 by 10 to the 16. 3 by 10 to the 8 squared, of course. We've got a number of 2.05 by 10 to the 8. Is that? Oh, hang on. Sorry. 3.276. Thank you. 3.276. I was jumping the gun there. Going to EV. Joules. You're going to get a value in joules, of course. That's how we do all calculations for energy. Change that to EV. So we take that number, answer divided by 1.6 by 10 to the minus 19 coulombs. 2.05. We get a value in EV. I'm going to write that. I'm going to rewrite that. 205 MeV. Is that right? Yes, the book says so. Yeah, okay, you got my joke. That's good. 205 MeV. How much? What have we done? Let's have a look. What have we done? We've just reacted one uranium nucleus to have one fission, one single fission, one nucleus is being split to create 205 million electron volts. What's the order of electron volts when we're talking about a chemical reaction? Chemical reaction. This is me having a go at the chemists. Chemical reaction, 100 EV per reaction, something like that. It depends on the energy stored up in the whatever it is that you're burning, but it's not. What are we talking about here? 1,000,000 times the energy per reaction. Yes. Now, don't quote me on that number exactly, but I know it's approximately 1,000,000 times. Yes. Okay. So this of the order of hundreds of EV for carbon reaction. So burning carbon. Hundreds of the order of hundreds of EV per reaction. What they say is that that uranium has a high energy density. You need very little of it to create a lot of energy compared to burning hydrocarbons. Okay. Oh, yeah. Only in a nuclear reactor. It depends on the size of the reactor. Yeah, of course, mate. Yep. Is in a nuclear reactor, how much of this stuff is going in? How much of this stuff are we putting into the nuclear reactor? It's of the order of kilograms. In a coal-fired power station, of the order of tons, hundreds of tons, of course. Okay. How does fission occur? What's going on? We have a neutron being fired into a large nucleus. What it does, when that neutron does that, we see it as it kind of creates it unstable and it elongates. Okay. So what are the consequences to this nucleus elongating, do you think? Yeah, it is vibrating, and it's vibrating by kind of stretching itself out. Think about the Coulomb force and the strong force. Your answer? When it once it elongates, look at the strong force. Strong force only works over a couple of nucleon diameters, but the coulombic repulsion works over a much larger distance. And so as it stretches out, that coulombic repulsion overtakes the strong force, and we have the nucleus splitting. Okay, so it becomes two smaller nuclei, two daughter nuclei. So nucleus vibrates. Yes, yes, but uncontrolled. We'll talk about that shortly. Nucleus vibrates and elongates. When it does this, the short range nuclear force or strong force no longer has effect or much effect on the outer nucleons. The long range coulombic repulsion. Yes. Yes. Long range coulombic electrostatic repulsion takes over and causes the nucleus to split into two approximately equal mass. Your book says lighter nuclei. Don't use lighter. It doesn't mean anything in physics. Approximately equal mass nuclei. Don't use the words heavy and light, please. Okay. Chain reactions. Oops. Chain reaction. I've got an applet that I'd like to show you as well, which shows a chain reaction. It shows a nuclear reactor and how it goes on inside a nuclear reactor as well. Make sure this is on. Yes, good. Let's see. So we know. What have I got there? Oh no, that's that. I want the. So we have a nucleus splitting into two smaller nuclei. approximately equal mass nuclei. And this is induced fission, so I'm going to say that there's a neutron being fired at that nucleus. And this occurs. We also have some more neutrons. What can these then go on and do? Yes? That's right, yeah. So what's going to happen is we're going to have, of course, other uranium nuclei in the area. It would be very rare that we have only one uranium nucleus. And those neutrons can go on and cause other fissions. Yes. Uh, Whoops. So this is the next reaction. And of course, these fissions, what do they do? Yeah, we have some more neutrons created. Not necessarily two, remember, but some more neutrons created. Now, yeah. So what's happening in this reaction eventually is, of course, so we're going to end up with some, for instance, barium and krypton in there with the uranium. That barium and krypton is they're isotopes of barium and krypton, and they are radioactive themselves. If these neutrons go on and strike these smaller nuclei are much more stable and almost completely unlikely to fission. And so what the nuclei will tend to do is either bounce off of them or pass straight through them. So this is what is called a chain reaction. Remember that these neutrons, I did this in yellow before. Not necessarily. Exactly. 1 to 2 million electron volts, the energies of these neutrons is too large, far too large. We have to slow them down. Essentially what that is 1 to 2 MeV of kinetic energy. Okay, so they're moving pretty fast, too fast in fact. They just pass straight through these nuclei. We have to slow them down. We have to put something in the way. And so what we do is we have what is called a moderator. And that moderator is made up of light nuclei, and I'm just going to draw heavy water here, or deuterium, it might be. Okay, so this here is the moderator. What happens when you strike a pool ball against a pool ball? Yeah, it gives energy to the other pool ball, doesn't it? What happens if you had a pool ball that was this big? I'm showing the size of bigger than a basketball. Size of a basketball, pool ball, and you struck your pool ball with your cue, normal size pool ball. What would happen when it hit the basketball sized pool ball? Bounce off, wouldn't it? It would bounce back. It's not going to pass much kinetic energy to the basketball sized pool ball, is it? That basketball sized pool ball is just going to sit there. It will move a little bit, but not very much. So that pool ball doesn't lose much kinetic energy. However, if you have nuclei that it collides with that are approximately the same size, or very light, rather low mass nuclei, then it's going to impart some of its kinetic energy to those low mass nuclei, and it's going to lose some and slow down essentially. Okay, so what we have is a moderator, which is made up of the moderator is low mass nuclei suspended in water. We call it heavy water. And it's not always, the things that I'm quoting here are the things that your text in this course describes. It's not necessarily how modern nuclear reactors work. The moderator, I know, in some situations can be a gas. So it's just what this course describes at the moment. And it's often what we are looking at, it seems, is old technology. Okay. So moderator is made up of low mass nuclei, which take much of the kinetic energy from the high velocity neutrons the neutrons need to have approximately, I think it's 1 eV, 10 eV, beg your pardon. 10 eV is fine. 10 eV of kinetic energy. And that's just velocity or speed, to cause further fissions. So I need to slow them down, and then they'll cause further fissions. And of course, there's a moderator in here as well, which will go on and cause further fissions. This is what is called a chain reaction, and I'll show you before I do, I'll just talk about U238 and U235. That will make things a little bit clearer as well. 238 and 235. What am I talking about? Isotopes of uranium, okay? This one here is much of the stuff that we dig out of the ground. So this is how we first get the fuel. It's about 99.7% U238. This is not good enough to cause fission, or to cause a chain reaction rather. And so it's 0.3% U235. We need to enrich it. Okay, so we do something called enrichment, which is a nuclear process, of course. We're changing this stuff into this stuff, and we get approximately 3% U235. Yes, I've put the mass number on the right-hand side. That's okay too. I should be consistent with that as best I can, but just so you know, you can write it that way. 3% U235. This is what is said to be fissionable fuel. We'll talk about a nuclear bomb in a second. Weapons grade. And lucky for us, this is hard to come by. Grade. Approximately 85% U235. Or plutonium. We won't go into that. Now, so it takes it takes a lot of energy to get this U-235 at 85%. Lucky for us, or lucky for our world, because there's some people that aren't necessarily very moral out there that would use this stuff to cause havoc around the world. And lucky for us, they can't get their hands on it. If they have the money to get their hands on it, we know, now with satellite technology, you need a big processing plant to be able to make this stuff, and they are very obvious. So, yes. Yeah, that's a good question. So essentially, now I've got a a nuclear reaction here. I'll just go to a new page. Now, your text doesn't have it though. Let me just confirm what I'm talking about, that I've got the right thing. Uranium enrichment. See if we can get a simple nuclear reaction. Actually, I should have left it on images maybe. Go to images, see what it shows us. Diffusion, sorry. What else is there? What's this one? Oh, I can't really read that. What's this one? Okay, natural uranium, 0.7% U-235, 99.3. So I've got the numbers the wrong way around. Sorry about that. Enrichment. So gas diffusion. So what they do is essentially the mass of this stuff is larger than the mass of this stuff. Can you see? So I can separate it by this diffusion process, because it kind of like gold panning, so to speak. Okay, think of it like that. And so what I can do is throw away the U-238 that's left over, and I've got a higher proportion of U-235 in that case. So that's low, and that will result in low enriched uranium, about 4%. More enrichment if you enrich it again. So same thing, centrifuge gas diffusion. So spin it around really fast and diffuse it through something. Highly enriched uranium. So this is weapons grade here. They're saying 90%. The data that I got last time I looked is around about 85% is considered weapons grade. Yeah, depleted uranium there they use in armor-piercing bullets. You will certainly have heard them talk about that in the movies. Yes, because it's particularly dense and very normal bullets will when they hit something very hard, they just kind of spread apart. Depleted uranium, being very dense and very hard, will not. They'll hold their shape and go straight through. So if they're very pointy and they hit something, even a Kevlar vest, they'll tend to go straight through it. Okay. Back to okay, a nuclear reactor. Now, I don't like this image that we've got here. I'll just have a look at, see if I can find a better picture for you. I'll just pause the video while we're looking. Here's an image of a very simplified image of what's going on inside a nuclear reactor at the core. This area here would be considered the core. Now, we have control rods, and we'll talk about those in a second. They've put them as neutron catchers. This is our fissile uranium. So this is the fuel, essentially. minimum 3% uranium-235, still a lot of uranium-238, and that percentage is important. If we put weapons-grade uranium in here at 85%, yeah, we fire a neutron into it, we've got a bomb, okay, so no good. Um, Around all of this stuff is a moderator. That moderator is, we teach that it's a liquid. It's usually heavy water deuterium to absorb some of those neutrons or absorb some of the energy of those neutrons. And we have these things called control rods, which can move up and down in between the fuel rods. Now, I'll try and find an actual image of what the fuel rods look like in a second. In through from the outside, so this is all contained inside a few centimeters, 10 centimeters of steel encased in a few meters of concrete. This is the radiation protection barrier, okay? So all of this is contained inside there. We do have some connection to the outside world through this water exchanger here. So water comes in here, cold temperature water or cool temperature water. It gets heated, superheated by moving through the moderator, and then it comes out at a higher temperature, creates steam, turns a turbine, makes electricity. Okay. Let's get a picture. I'll just pause of the actual. Inside that, they place the U238, U235 mix, and they then become the fuel rods. This device itself, so this structure here that kind of looks like a big rectangular prism, that structure, of course, allows the moderator to go in between the fuel rods. The liquid itself can go in and fit between those fuel rods, so that the neutrons that are created in each fuel rod can be slowed down between the fuel rods and go on to cause further fissions. Okay, so I might just that's just as a matter of interest. What doesn't it like about that? Okay, let's have a look at something that I've put up on our Moodle. Here's a chain reaction occurring. This is from the University of Colorado FET simulator. Okay, so I'm going to fire a neutron into that U235. It gets excited, splits apart. Okay, let's do it again. I'll just show you that again. Neutron becomes U236 for a second, splits into two daughter nuclei, releases 3 neutrons in this reaction. Notice again, this is the energy, the nucleus energy, and across here, this is the distance. So there's 0. That's where we're starting from. The distance between the daughter nuclei are going left and right. I'll just show you one more time. Gets excited, vibrates crazy. Let's do a chain reaction now. I'm going to increase the number of U238. Now, this doesn't exactly work in proportion. What we tried to do yesterday in Year 11 physics was get three nuclei for U235 and 97 for U238, and this program isn't really set up like that. So we fire a neutron. We haven't got a chain reaction occurring there. Okay, what we have to do is we're going to increase the proportion of U235, and we might see a chain reaction occur. Okay, so the chain reaction starts, doesn't keep going. Try again. There we go. Okay, we need to increase the. Let's have some more U235. Okay, little bit of a chain reaction going on there. The looks things. Okay, you can see it's not particularly easy to achieve a chain reaction that is controlled. And if I just made it all U235 and no 238, of course, we've got something which could go out of control very quickly. Okay, and we're looking at nuclear bombs. Here's a nuclear reactor, a simplified view of a nuclear reactor. These are little U-235, U-238 nuclei. So these are the fuel rods, these light blue things here. These are the control rods, okay? And they're immersed in a moderator, of course, to slow down those neutrons, remember. If I fire a neutron, okay, so we can cause some fissions there, of course, but they don't keep going. What I have to do is I have to move the control rods out a little bit and see if we can get a chain reaction that occurs without going out of control, too much heat, but also I'm going to move them out again now. Okay, so these control rods are probably controlled by a computer. All that humans do at these nuclear facilities is they make sure that the computer is doing its job correctly and nothing goes wrong. Okay, thank you.